Hi, I'm Prof L and welcome to Chemistry Matters. And today we are going to be looking at stoichiometry problems and in particular looking at how we use balanced chemical equations when we're looking at stoichiometry problems. Right, so let's kick off by looking at an example of a balanced chemical equation. And the one that we are going to be looking at here is this one here. This is the production of ammonia from nitrogen and hydrogen. Hopefully it interests you to know that this particular chemical reaction actually takes up 1 to 2% of the total energy that is produced on planet Earth every year. And if that doesn't make you go, wow, then nothing will. An extremely important equation, this one, and for the production of ammonia, and ammonia is used in fertilizer, which is why this is so important. This is an example of a balanced chemical equation. What do we mean by balanced? We mean that there are the same number of atoms of each type on both sides of the balanced chemical equation, on both sides of the arrow. So if we count them up, we could say, right, we've got a nitrogen molecule here that's made up of 2 nitrogen atoms. On the right-hand side, we've got 2 ammonia molecules. Each of those contain 1 nitrogen atom, so we've got a total of 2 nitrogen atoms here, 2 nitrogen atoms here, balanced. On this side, on the left-hand side, we've got 3 hydrogen molecules. That's a total of 6 hydrogen atoms. On the right-hand side, we've got 2 ammonia molecules. That, again, is a total of 6 hydrogen atoms because each ammonia molecule contains 3 hydrogen atoms. Now, what does the balanced chemical equation tell us? It tells us, most importantly, the mole ratio in which reactants react to give products. Okay, let's wind that back just a step. A balanced chemical equation also tells us what's going on the molecular level. So this is saying that if we talk about molecules, 1 nitrogen molecule is going to get together with 3 hydrogen molecules to form 2 ammonia molecules. Okay, that's on the most fundamental level, on the absolute microscopic level. But let's come up to the macroscopic level, the everyday level, where we're talking about grams of material and not 10 to the minus 24 grams of material. What this balanced chemical equation also tells us is that 1 mole of nitrogen will react with 3 moles of hydrogen to produce 2 moles of ammonia. And that's what I meant by this whole mole ratio thing. So, nitrogen and hydrogen always react together in a mole ratio of 1 to 3. Now, that's a really, really important concept. Okay, so that is what balanced chemical equations are very, very useful for when it comes to stoichiometry problems. So, this whole mole ratio thing that is encompassed within this balanced chemical equation is basically telling us that for every mole of nitrogen that reacts, we're going to require 3 moles of hydrogen. Okay? Now, let's assume that this reaction proceeds to completion. In actual fact, it doesn't, but we're just going to assume that it does. And therefore, if we had 1 mole of nitrogen, it would then react completely with 3 moles of hydrogen, and at the end of the reaction, we would have 2 moles of ammonia. Okay, and we can see that straight away from what we call the stoichiometric coefficients in this equation. In other words, the numbers that come before our reactants and products. They are called, in fancy terms, stoichiometric coefficients. And we can see that straight away. 1 mole of nitrogen will react with 3 moles of hydrogen to give us 2 moles of ammonia. Now, that's nice and straightforward. Where it starts getting complicated and where people have trouble is when the actual amounts that we're using don't correspond exactly to these numbers. This is fine, provided we start with 1 mole of nitrogen. We can see that we've got a mole ratio of 1 to 3. Instead of, let's say, starting with 1 mole of nitrogen and 3 moles of hydrogen to get our reaction going, what would happen if we started not with 3 moles of hydrogen, but with 5 moles of hydrogen? What then happens? How much nitrogen are we going to need for complete reaction? And how much ammonia are we going to get formed from this particular reaction if we start with 5 moles of hydrogen? And this is where 90% of the problems come with students in stoichiometry, is this whole mole ratio thing, okay? We know we've got a mole ratio of 1 to 3 here, okay? So if we've got 3 moles of hydrogen, it's going to take 1 mole of nitrogen. If we've got 5 moles of hydrogen, we know what the mole ratio is. We know it's a 3 to 1 mole ratio, but where students often go wrong is that they don't know whether to multiply by 3 or divide by 3. Okay, so again, I'm going to show you a little trick that is going to help you immensely to remember all of this, to get this round the right way. Okay, so let's look at a general chemical reaction. So we're going to say A moles of A plus B moles of B is going to react to give us C moles of C and D moles of D. So here's something to remember, that the number of moles of A over little a is equal to the number of moles of B over little b is equal to the number of moles of C over little c is equal to the number of moles of D upon little d. And again, that's so important, I'm going to put it in a red box. Now, this looks complicated, and you're thinking, do I have to learn that? Well, yes and no. It actually looks more complicated than it really is. All that we're saying is that you take your number of moles of A and divide it by the stoichiometric coefficient. Remember, this is the number that comes in front in your balanced chemical equation. We take the number of moles of B and divide it by that stoichiometric coefficient, etc., etc. And for a balanced chemical equation, this is true. The number of moles of A divided by A is the number of moles of B over B, is the number of moles of C over C, is the number of moles of D over D. Now, again, you're still thinking, gosh, do I really have to learn that? Well, no, you don't, because let's go back to that example that we had and let's now use this. So again, keep this in your mind and let's go back to our example of nitrogen plus 3H2 going to 2NH3. We said, right, we're going to start with 5 moles now of hydrogen. How much nitrogen are we going to need? How much ammonia are we going to form? Again, remember, assuming that the reaction goes to completion. So from what we had on the whiteboard before, that big scary looking equation, we can then say that the number of moles of N2 divided by the stoichiometric coefficient of nitrogen is 1 is equal to the number of moles of H2 divided by stoichiometric coefficient 3 is equal to the number of moles of ammonia divided by stoichiometric coefficient 2. So this is true regardless of whether we're looking at the reactants or the products. This is always true. So we're going to say, right, we're going to start off with 5 moles of hydrogen. How much nitrogen are we going to need to react completely with that? So let's just concentrate on this bit here. We're saying the number of moles of nitrogen divided by 1 is equal to the number of moles of hydrogen divided by 3. So therefore, the number of moles of nitrogen, this is what we're after, is equal to the number of moles of hydrogen divided by 3. Now we know we're starting with 5 moles of hydrogen, so therefore the number of moles of nitrogen that we need is going to be number of moles of hydrogen, which is equal to 5 divided by 3. And there's your answer, okay? So in this case, knowing this mole ratio, we are going to take our number of moles of hydrogen and we're going to divide it by that mole ratio, that 3:1 mole ratio, okay? So we start with 5 moles of hydrogen. In order to get complete reaction, we're going to need 5/3 moles of nitrogen in order for complete reaction. What about the number of moles of product that we're going to get out of this? Again, remember, assuming that the reaction goes to completion, we're going to say, right, so our mole ratio of interest here now is the mole ratio between the number of moles of hydrogen and the number of moles of ammonia. So the number of moles of hydrogen over 3 is going to be equal to the number of moles of ammonia divided by 2. Therefore, the number of moles of ammonia is going to be equal to 2 times the number of moles of hydrogen divided by 3. And let's make some space. So the number of moles of ammonia is twice the number of moles of hydrogen upon 3. So therefore, number of moles of ammonia is going to be equal to 2 times 5/3, which is equal to 10 divided by 3 mole of ammonia. Okay, so that's what we're going to get out of this particular reaction. So that is a really, really, really important concept. This whole idea of whether you have to multiply or divide when it comes to figuring out the number of moles of reactant or product that you need or are going to get in any particular chemical reaction. Now, we're going to come back to this concept again, and we're going to look at it in terms of not moles, which is what we've been doing all the time here, but we're going to look at it in terms of masses, which is obviously what we use in the laboratory. So then, how do we take this concept and apply it to masses? Well, we're going to look at that in a subsequent video. So, hopefully you've got your head all around this. We'll see you next time.